Today's lecture is going to be about an intermediate integration technique called integration by parts. The good news is, when it comes to integration by parts, we only have one formula to worry about, which is this one right here. So we have integral of u dv, which can be found from u times v minus integral of v du. That is it. That is the only formula for integration by parts. However, you need to keep in mind that we have two types of integrals. The first one is indefinite, where we have no boundaries, no starting or end points. The other one is definite, where we have starting and the end point, a and b. For indefinite integral, we find antiderivative of some function. So in the end, we always expect to see a constant c to show up. So for this one, indefinite integral, expect to see constant c, which should be right here, plus c. So even though sometimes you don't see this plus c at the end of this formula, you sort of know it's there if you perform indefinite integration by parts. And now for definite integral, we expect to see a starting point a and the endpoint b, which should show up right here, integration from the starting point a to the endpoint b. And this a and b has to appear on the right-hand side of this formula too. So u times v that we have right here is not just uv. It has to be evaluated at two values, b and a. So this has to be evaluated at b minus evaluated at a. So let's make a note right here that this is u times v evaluated at b, the endpoint, minus u times v evaluated at a, the starting point. And now for the integral back here, it's the same thing. We integrate from the starting point a to the endpoint b. And there you go, we now have two variations of the same formula for integration by parts. The first one is indefinite integration by parts, and the second one, definite integration by parts. Well, using a formula without knowing why it works is not a good thing. So let's take a look at the proof of the formula for integration by parts down here. It only takes just a few minutes to finish. Let's begin now. First of all, let's assume that we have two different functions. First one, f of x, and g of x, the second function. They are different functions. Let's also assume that we have a product between them, between f of x and g of x. So we have f of x times g of x. And now we want to differentiate this product with respect to x. To find this, we need the product rule. So let's make a note up here that we need product rule. So it's going to be front diff back plus back diff front. So the front function is f of x and the back function is g of x. So front f of x, diff back, we have g prime of x, plus back, which is g of x. Diff front, we have f prime of x. And now the next thing we are going to do is to integrate both sides of the equation with respect to x. Integrate and dx back here. On the right-hand side, same thing. Integrate all these terms with respect to x. Integration and dx back here. Also, let's assume that these integrals are indefinite. So this one on the left-hand side is indefinite. Same thing on the right-hand side, indefinite. No boundaries, no starting and end points. Now let's take a look at this on the left-hand side. We differentiate this product between f of x and g of x, and then we integrate the result of that at the end, right here. So we diff first and then we integrate later. As you can see, these two sort of cancel each other, and this means that we are supposed to get the product back, f of x times g of x down here. However, you need to keep in mind that the last operation that we performed is indefinite integral, which means that we are supposed to get a constant c showing up at the end. So we are supposed to have this plus c at the end. Now let's work on the right-hand side of this equation. On this side, I'm going to distribute the integration to the front term, f of x times g prime of x, and then distribute this to the back term, g of x times f prime of x. And now we integrate them separately. And now we have two integrals. The first one is integral of f of x times g prime of x. And we integrate this product with respect to x dx right here. Plus the second integral, the back term. We integrate g of x times f prime of x, and now we integrate this product with respect to x dx right here. Now let's move things around so that this first integral can be alone on the left-hand side. So let's put it right here. Integral of f of x times g prime of x dx. It's going to be equal to the other side of the equation. So we have these terms, f of x times g of x. And don't forget the constant c. So let's put it right here. We have f of x times g of x plus c right here. And now we move the second integral to the other side. So we have minus integral of g of x times f prime of x dx. At this point, let's do this on the right-hand side. Let's assign u a new variable to be equal to the first function, f of x. And then we assign v another new variable to be equal to the second function, g of x. And now I diff u with respect to x, du by dx, I get first order derivative of f, and that is f prime of x. And same thing down here, I diff v with respect to x, I get the first order derivative of g, that is g prime of x. And now I move dx to the other side, I have this du equal to f prime of x times dx. And down here, same thing. Move dx to the other side, to the right-hand side, I have this dv equal to g prime of x dx. Now that we know that u is equal to f of x and v is equal to g of x, let's put them in the equation. Looking at the equation, I can see f of x right here and also here. So I can use u right here for f of x and also here. For g of x, I can see 1 right here and also here inside the integral. And I can use v for g of x and also here v. Now back to the right-hand side. We also know that dv is equal to g prime of x dx. And I can see these terms right here, g prime of x dx. So I can use dv right here. And now last one, we know that du is equal to f prime of x dx. And we can see these terms down here on the right-hand side, f prime of x dx. So we can use du right here. Now let's put everything inside this equation together and express it in terms of u and v. And now we have this integral of u dv right here. U dv equal to u times v, u dot v minus integral of v du. And there you go, we just derived the formula For integration by parts, as you can see, it all comes down from this product between f of x and g of x and the product rule of differentiation. The question is, when should we use integration by parts? And the answer is, it's hard to know beforehand whether integration by parts is the way to actually solve the problem, unless you try it and see if it works or not. However, I have this guideline for you so that you know when to consider integration by parts. Guideline number 1. You can consider using integration by parts when all other basic techniques failed. So let's make a note right here. When other basic techniques failed. What kind of basic techniques are we talking about here? Let's take a look. Number 1, we are talking about basic anti-derivative rules. Number 2, substitution. So if these two failed, both of them, you may try integration by parts. And now the second guideline. You may try using by parts when you see this pattern inside your integral. This one. A product between two functions inside your integral. So let's make a note down here that we may try using by parts when it's an integral with a product of two distinct or different functions. So if you see this pattern, a product between two different functions, like this, f of x times g of x, inside an integral, then it's a good candidate for integration by parts. Keep in mind that this guideline is not a guarantee that by parts is gonna work. Let's make a note right here. Not a guarantee. So in the end, you're gonna have to try and check it yourself. Now, at this point, we know that we have a product of two different functions inside our integral. And then we want to use this formula for by parts. Integral of u dv. And now the next question is, how do we choose which function to be u and which to be dv? And once again, the answer is, it's hard to know beforehand unless you try and check it out. However, I have this guideline for you on how to pick u and dv. Number 1, you pick u that can be differentiated. Why is that? Let's take a look at the formula at the top left, right here. So we start out with this integral of u dv. Notice that we have u inside this integral, right here. And somehow this integral is too hard to solve, so we decide to use by parts formula on the right-hand side. This one, u times v minus integral of v du. As you can see, in order to use this formula, we need this. We need du. Without this du, we cannot continue with this calculation. So, starting out with u, and we need du later. This means that the u that we pick must be possible to differentiate it. So, let's add down here that u can be differentiated to get du. For the formula. And now the second guideline, number 2. pick dv that can be integrated. Once again, let's take a look at the formula at the top left, the same one. So we start out with this same integral of u dv, and we have this dv inside our integral. And then we decide to use by parts formula on the right hand side, this one. Same formula, and you can see that we have v right here in the formula, and also here. This means that in order to use this formula we need v. So we start out with dv, and then we need v later inside the formula. So this means that dv that we pick must be possible to integrate. So let's make a note right here. dv can be integrated to get v for the formula. Now, sometimes you may run into a situation where both u and v can be differentiated and integrated. In that case, how are we supposed to choose u and dv? And here comes the third guideline, number 3. Pick u such that du is simpler than u. Now back to the formula up here again. As you can see, inside this formula we have this du. We need this du for the calculation. This means that it would be nice for du to be simpler than it was before, so that the calculation may be easier to perform. So let's make a note down here that we prefer du to be simpler, not more complicated than u, so that we have easier calculation. Now let's try integration by parts on some examples in the next slide. Example number 1. We need to integrate x times e to the power of x. First of all, we can see that we have an integral with a product between two different functions, which are x and e to the power of x. When you see this, you know right away that this is a good candidate for integration by parts. So let's try by parts for this integral. So it's going to be this formula, integral of u dv equal to u times v minus integral of v du. And now we need to pick one function to be u and the other to be dv. So let's try this. Let's set u to be the first function equal to x and dv to be the second function e to the power of x dx. And now we check 3 guidelines. G1, u can be differentiated. G2, dv can be integrated. And G3, du is simpler than u. Now let's check G1 by differentiating u with respect to x. It's going to be equal to, we diff this x with respect to x, we get 1. Since we can differentiate u here, it means that G1 is satisfied. So let's check right here. From this, we also know that du is equal to dx. And now let's check G2. Let's try to integrate dv. So integrate dv is going to be equal to integral of e to the power of x dx. Now we find the antiderivative of e to the power of x. And we know that it stays the same. So we have e to the power of x right here. And this is going to be equal to v. Since we can integrate dv, it means that the second guideline is satisfied. So G2, check. Now let's check the last guideline. Is du simpler than u? du by dx is equal to 1, a constant. U is x, a polynomial. 1 is simpler, which means that du is simpler than u, which is good. And this means that the third guideline is satisfied. G3, check. Now let's put everything together on the right-hand side. So we know that u is equal to x, and v is equal to e to the power of x. Du is equal to dx, and dv is equal to e to the power of x times dx. And now we have an integral of u dv, u is right here, equal to x. And dv is right here, equal to e to the power of x dx, equal to u dot v, u once again is equal to x, times v, which is right here, e to the power of x, minus integral of v, which is right here, e to the power of x, and du is right here, equal to dx. Now it's going to be equal to. The first term stays the same. So we have x times e to the power of x, minus, now we find the antiderivative of e to the power of x, right here. And we know that it stays the same. Same e to the power of x. As you can see, this is indefinite integral. It means that we must have a constant c at the end. Now let's take the common term to the front. E to the power of x times x minus 1, and don't forget to have the constant c at the end. And that is the answer for example number 1. Now let's move on to example number 2, down here. We need to integrate x cubed times ln x. As you can see, once again, we have to integrate a product between two different functions. In this case, they are x cubed and ln x. When you see this, you know it's a good candidate for integration by parts. So let's try that. Same formula. Integral of u dv equal to u times v minus integral of v du. And now we need to determine which function to assign to u and which to dv. We also need to check 3 guidelines. G1, u can be differentiated. G2, dv can be integrated. And G3, du is simpler than u. So let's try this one. U equal to the first function x cubed and dv equal to the second function ln x dx. Now let's check G1. Let's try to diff u. Du by dx, we have 3x squared. U can be differentiated, so G1 is satisfied. Check. Now we check the second guideline, G2. Let's try to integrate dv. Integrate dv equal to integral of ln x dx. And now we need to find the antiderivative of ln x. It's going to be equal to, well, what is it equal to? Antiderivative of ln x. So far we know that if we diff ln x, we get 1 over x. But we don't know what do we get when we integrate ln x. So at this point, we don't know. And this means that the second guideline is not satisfied for this choice. So this is not a good choice. We cannot assign this. Not good. Also this one. We cannot use this. And now we have to try the other choice. U equal to ln x. And dv equal to x cubed dx. Now we need to check G1 again. Let's diff u. du by dx equal to, now we need to diff ln x, and we know we have 1 over x. Since we can diff u, g1 is satisfied, so check right here for the second choice. For g2, let's try to integrate dv again, equal to integral of x cubed dx. For this one, we have to find the antiderivative of x cubed. And we know it's equal to x to the fourth divided by 4. And this is equal to v. So we can integrate dv. It means that g2 is satisfied. This one is good. Check. Now for g3, we need to check whether du, which is equal to 1 over x, is simpler than u, which is equal to ln x. Is 1 over x simpler than ln x? Well, sort of, but not that simpler. So I would say that it's just okay. Not that simpler, but not bad. At this point, we know that guideline number 1 is satisfied. We can differentiate u. And guideline number 2 is also good. We can integrate dv. Guideline number 3 is okay, not that simpler, but acceptable. This means that we can continue with the calculation of integration by parts. So let's do that on the right-hand side. So we have u equal to ln x and v equal to x to the fourth divided by 4. Du equal to dx over x. And now last one, dv equal to x cubed dx. Now back to the formula. Integral of u dv. U is equal to ln x. dv is equal to x cubed dx. Equal to u times v. U is ln x. And v is x to the fourth divided by 4. Minus integral of v du. V is x to the fourth divided by 4. And du is dx divided by x. Let's cancel these two, x right here and 4. So we have x cubed instead. Let's evaluate this. Equal to, the first term still the same. So we have ln x, x to the fourth divided by 4, minus, now we have to find the antiderivative of x cubed divided by 4. We have x, and the power increases by 1, so we have 4, divided by the same number down here. And don't forget that we have another 4 right here. So let's bring it down. Divided by another 4, right here. Once again, this is indefinite integral, so we must have a constant c at the end, plus c right here. Now let's make it look nicer. Equal to the common term at the front, x to the fourth divided by 4. Inside the parentheses we have ln x minus 1 over 4. And we have plus constant c at the end. And that is the answer for example number 2. Let's move on to the next slide. In this example, we need to integrate x squared times sine x. Once again, we have a product between two different functions. In this case, we have x squared and sine x. And now when you see this, let's try by parts. Same formula, integral of u dv equal to u dot v minus integral of v du. Just like before, we need to check 3 guidelines. G1, u can be differentiated. G2, dv can be integrated. G3, du is simpler than u. And now we need to choose a function to be u and the other to be dv. Let's try this one first. The first function x squared for u and the second function sine x dx for dv. Let's check g1. Let's diff u with respect to x. Diff this, we get 2x. So u can be differentiated. g1 is satisfied. Check. Now let's integrate dv equal to integral of sine x dx. Now antiderivative of sine x, we get minus cosine x. And this is v. So dv can be integrated. g2 is satisfied. Check. Now g3 is du, which is equal to 2x simpler than u, which is x squared. So 2x power of 1 is simpler than x squared power of 2. So yes, simpler. g3, check. From this, we also know that du is equal to 2x dx. And now we know that u is equal to x squared. du is equal to 2x dx. dv is equal to sine x dx. And last one, v is equal to minus cosine x. And now we put everything together on the right hand side. Integral of u, and that is equal to x squared. dv equal to sine x dx. So let's put it right here. Equal to u dot v. u is x squared. v is minus cosine x. So let's put them together. We have x squared times minus cosine x minus integral of v, which is equal to minus cosine x. And then du, which is equal to 2x dx. The first thing I'm going to do here is to take minus sign to outside the integral, and also a constant 2 right here to outside. So we should have plus 2 right here. Now let's evaluate the whole thing. Equal to the first term, minus x squared cosine x, plus 2, the new coefficient. And now we have integral of x cosine x dx. It's going to be equal to, same term, minus x squared times cosine x, plus 2. And now we need to find antiderivative of x cosine x. What is that equal to? Integrate x cosine x. We don't know. It's not easy to integrate. So let's make a note right here that we don't know the antiderivative of this term. However, we can see that this is a product between two different functions, between x and cosine x, which means that this is a good candidate for biparts. So let's add right here that we have a product between two different functions. Again, with this, we know it's biparts once again. So here we have second round of biparts with two functions, x and cosine x. This time, once again, we check g1, g2, and g3. Just like the first round, we need to assign a function to u and the other to dv. So let's try this. U equal to the first function x and dv equal to the second function cosine x dx. And now we check g1. Diff u with respect to x, we get 1. So u can be differentiated, which means that g1 is satisfied. Check. For g2, let's integrate dv. It's going to be equal to integral of cosine x dx. And now we find the antiderivative of cosine x. And we know it's equal to sine x. And this is v for the second time. So dv can be integrated. g2 is satisfied. Check. Now for g3 is du, which is equal to 1. Simpler than u, which is equal to x. Is constant 1 simpler than x? Of course, this is simpler, a constant. So g3 satisfied. Check. With this, we also know that du is equal to dx. And now we have u equal to x, du equal to dx, dv equal to cosine x dx, and v equal to sine x. Let's do the second round of by parts on the right-hand side. So we have integral of u, which is equal to x, dv equal to cosine x dx, equal to u times v, u equal to x, and v equal to sine x times sine x, minus integral of v, which is equal to sine x, du equal to dx. Let's evaluate this. Equal to the first term, same thing, x sine x. And now we need to find antiderivative of sine x, and we know it's minus cosine x. This is indefinite integral. Also here, indefinite. We must have a constant c at the end, plus c, right here. So in the end, for the second round of by parts, we have x sine x plus cosine x plus a constant c. And now we put all these terms to here. And now we have x sine x plus cosine x plus c. And now the last step, we have minus x squared cosine x plus 2x sine x plus 2 cosine x plus 2c, which is also a constant. So let's use c for that again. And that is the answer for example number 3. Let's move on to the next slide. In example number 4, we need to integrate x squared times sine of 2x cubed. Once again, we have a product between two different functions. This time it's x squared and sine of 2x cubed. And now we see this, we want to try by parts. Now, before you jump into that conclusion, let's try something simpler and easier method, and that is basic substitution. So let's try this. Try basic sub technique before we continue with the fancy process of integration by parts. So I see this chunk, 2x cubed, inside sine. I want to make this simpler. So let's make it u. And now we have u equal to 2x cubed. Let's differentiate this. Du by dx. Diff this, we get 6x squared. And now we know that dx is going to be equal to du divided by 6x squared. Now let's continue our calculation on the right-hand side. So we have an integral of x squared times sine of 2x cubed dx equal to integral of x squared sine of, and now u goes in right here, dx. As you can see, we have the new variable u right here, but we still have x inside our integral right here and right here. So let's do something with this dx. Let's change it to be in terms of u. On the left-hand side, we know that dx is equal to du divided by 6x squared. So let's put it right here. And now we have integral of x squared times sine u. dx is equal to du divided by 6x squared. And as you can see, maybe we got lucky. This x squared cancel with this one. And now I'm going to move this constant 6 to outside the integral. Right here. Becomes 1 over 6. And now I have 1 over 6 at the front. Integral of just sine u. du. Let's continue right here. Equal to 1 over 6. Now we need to find the antiderivative of sine u, and we know that it's equal to minus cosine u. And since this is indefinite integral, also here, indefinite, we must have a constant c at the end, plus c. At this point, we have u inside our expression. But the original problem is in terms of x, as you can see here. This means that we need to sub back so that we can get x back. Now we have minus 1 over 6 at the front, cosine u, and u is equal to 2x cubed. And don't forget the constant c at the end. And that is the answer for example number 4. Before we move on, let's take a look at this. Just because you have a product between two different functions inside your integral, it doesn't mean that you have to use by parts every time. So let's add right here that you may try by parts, but it's not guaranteed. To work. Let's also make a note down here that sometimes an easier method like basic sub can solve the problem as well. This is telling us that we should try the easier one, like basic sub, before trying by parts. And now we move on to example number 5, last one. We need to integrate ln x with respect to x, and we want to use integration by parts on this one. At this point, you may wonder, we don't have a product between two different functions here. How can we use by parts? Ln x is actually equal to ln x times 1, a constant. In this form, we have a product between ln x and 1. And now we have a product between two different functions, which are ln x and a constant 1. With this pattern, we may try integration by parts. So once again, 3 guidelines. G1, g2, and g3. And now we pick one function to be u and the other to be dv. Let's try this. Let's assign the first function ln x to be u and the second function 1 times dx to be dv. And now we check the first guideline. Let's diff u with respect to x. Diff ln x, we get 1 over x. So u can be differentiated. g1 is satisfied. And now for g2, we integrate dv. And we have integral of 1 dx, which is equal to just x, and that is v. So dv can be integrated, which means that g2 is satisfied. And now for g3, we need to check du, which is equal to 1 over x, whether it's simpler than u, which is equal to ln x. Is 1 over x simpler than ln x? Well, sort of, but not that much simpler. Which means that for g3, I'm gonna say it's just okay. With this, we also know that du is gonna be equal to dx over x. And now we know that u is equal to ln x. Du equal to dx over x. dv equal to 1 times dx, or basically dx. And now v equal to x. Let's continue on the right hand side. So we have integral of u, which is equal to ln x. dv equal to dx equal to u times v. U is equal to ln x and v is equal to x. So u dot v is x ln x minus integral of v, which is equal to x. Du equal to dx over x. And now this x cancels with this one. So we only have integral of dx right here. And this is going to be equal to the front term, still the same, x ln x, minus, and now we need to find this integral of dx, and that is equal to just x. And once again, we have an indefinite integral right here. And also here. This means that we must have a constant c at the end, right here. Now take the common term x to the front. We have x times ln x minus 1 inside the parenthesis, plus c, and that is the answer for example number 5. With this, we know that x times ln x minus 1 is the antiderivative of ln x.